Hi, today's video is about compressor datasheets. In the previous session, a simple compression loop was simulated with no equipment data, and from today for about 20 videos, we developed the simulation and the design. Here are 6 hypothetical cases for the inlet feed gas is given from 2035 to 2040. In general, we don't have input for the compression loops alone. We have production facilities that defines the rates to each compression loop. But this is a simulation just to illustrate how to design the different equipments in the compression loop and not considering the whole upstream and downstream processes. Based on this schematic, I want to mention a few points. First of all, constant pressure drop is considered, which is not realistic. By changing the volumetric flow, the pressure drop in the cooler also varies. Later, we introduced resistance factor in the cooler to precisely or more accurately calculate the pressure drop. The target of the process datasheet for this session is a variable speed compressor. In addition, piping and fittings are not considered in this simulation. Here you can see a compressor curve for a variable speed compressor. If it was a fixed speed compressor, you would have only one curve. But for variable speed compressors, we will have an operating envelope. So starting from the minimum speed, and at the top we have the maximum speed. So between these two speeds, we have infinite speeds. So based on the pressure head and volumetric flow, the operating point can change, and therefore the speed will change. The line on the left is the surge line, which defines the unstable operation line. So we should avoid to go to the left side of this surge line. We typically have surge control line, which have around 10% margin to keep the operation safe and be far from the surge line. On the right side, we have a stone wall, which defines the upper limit in the flow rate. Here are the mapped cases in the polytropic head and actual volumetric flow rate plot. So which cases to be selected for the datasheet? My selection is 2035 as the design case, simply because this one defines the maximum speed of the compressor. 2040 is clearly the minimum flow rate case. 2039 likely defines the minimum speed. And 2035 is just to refine the operating envelope to optimize the compressor curve. This operating envelope or compressor curve is what I will expect to get from a vendor if I send a datasheet based on this operating point. So it might change and it might be smaller or wider, but it's all depends on the design, and vendor can provide you more information about this. What to include in the compressor datasheet? In general, we start with general info, like tag number, PNID, location, manufacturer, supplier, type, etc. Later, we need to mention the flow rates for different cases, followed by suction and discharge conditions, and also performance of the compressor. What we will include in the performance of compressor in the datasheet, they are just a calculated number based on our assumptions. So later, the vendor, based on their designed compressor, they can revise the performance data as well as discharge condition. In another page, we typically include composition and also hypothetical components properties if we have any hypothetical component in the composition. And finally, we have the notes at the bottom of the compressor datasheet or any other datasheet. So the nodes can be project specific or any other limits or criteria. So the vendor should be aware of it to provide you with the optimal compressor design. We need to mention there. This slide highlights the key data required for a compressor datasheet. It starts with the general info, similar to any other process datasheet, followed by specific data for a compressor. In this example, we have selected 4 representative operating cases to illustrate the datasheet structure. The specific data for the compressor start with the data which is similar in both suction and discharge side, like volumetric flow as standard condition, mass flow without recycle, corrosive compound, and molecular weight. Recycle flow, since we have no compressor curve available at the moment, we have to set it 0. Based on our composition, the gas handle was hydrocarbon, so we can set hydrocarbon for all the cases. And recycle flow, as mentioned, 0. And the corrosive components, we have water and CO2. You know that water, CO2 in the presence of water creates a corrosive environment. The next data is the suction and discharge condition parameters, such as operating pressure and temperature in both suction and discharge side, actual volumetric flow and density on the suction side, and also the specific heat ratio for both suction and discharge side. And the last one is the performance of the compressor. The performance calculation and some of the parameters in the discharge condition are estimated values, and they will be revised based on the vendor design and the given compressor curve. The next slide is about composition. So the composition should be also added for each of the selected cases in a separate page, typically in the datasheet, followed by the notes related to the datasheet. We can have many notes. Some of them are general and some of them are specific to the project. Typically, we have some notes like the performance data is calculated by the assuming a certain efficiency, and vendor should revise the data or update the values based on their design. Another thing is like adding the limitations. You know, in the previous session, you remember we had a discharge temperature limitation of 135 degrees centigrade, and we considered 5-degree margin, so 130 degrees centigrade is the limit for the design of the compressor based on our given design cases. Exercise that demonstrates how to map operating cases and locate the process data required for a compressor process datasheet using our examples. This is the simulation which is made in the last session, and it was for the design case, and I labeled it at 2035, and you can see also the other cases here. So before making the other cases, I need to write down 2 parameters. Actual volumetric flow on the suction side and polytropic head. I need this data for the mapping. So now I can save 2036. So for 2036, the flow rate is the same, and also suction pressure all the same, and composition you can see no change compared to year 2035 for our example. And the only difference is the discharge pressure of the compressor. So we are not going to find out the discharge pressure corresponding to any temperature for this case. So we have the discharge pressure available. So we put that value, which is 55 here. Now I can, you see the flow rate because we haven't changed the suction condition. So the flow rate is the same, volumetric flow rate on the suction side. And the polytropic head. is 107.2. So this is case 2036. For 37, the composition is different, flow rate as well. So flow rate 4.5. And one thing you need to also check in your simulation, you see that recycle is not didn't converge. The reason for that is we reduce the sensitivity, which requires more iteration. So in numericals, you can increase the number of iterations and continue. So the suction condition for the feed gas, temperature is the same, pressure is 18, and composition is also different. And finally, the discharge pressure. Now I can write down the parameters I need. I repeat the same for all other cases. No change in the composition until 2039. In the last case. So now we have all the data we needed to map the cases. Make the point a bit larger, the markers. Now we map the cases, and it can be used for further analysis, for case selection for the datasheet, and also we can put it on the datasheet on the node side. Now let's look at the data extraction from the simulation for the process datasheet. Let me bring that presentation slide. Yes. The first row of the information about the gas handle, here in the composition, we have the hydrocarbons, including some nitrogen, CO2, and H2O, but the majority is hydrocarbons. So the gas handle, you can write hydrocarbon. Volumetric flow has standard condition, which is the same between from suction to discharge side of the compressor. You can find it in the compressor section or the discharge. Let's go to the compressor section. In the properties and standard gas flow. You may ask why the standard volumetric flow is 1.9, but the input for the feed gas was 2. The reason is after cooling in the cooler, some of the heavy hydrocarbons condensed and become liquid and separated in the scrubber. So around 0.1 million standard cubic meter condensed as liquid and separated, and 1.9 million standard cubic meter per day is what entering the compressor. The next one is the mass flow rate. You can also find it in the worksheet tab and the conditions. Corrosive recycle flow. There is no recycle flow for our case because we don't have any compressor curve to quantify the recycle rate. So here, for such cases, we put the recycle flow 0. We never quantify recycle flow if we don't have any information about the compressor. Corrosive components. In the component list here, combination of CO2 and water creates a corrosive environment. So CO2 plus water is what you need to write it here. Molecular weight and the properties, you can find the molecular weight. Regarding the suction condition, we are already on the suction stream. Pressure and temperature, you can find in the condition subtab of worksheet tab. So here, pressure and temperature, actual volumetric flow, density, heat specific ratios, and compressibility factor, all of them you can find in the properties subtab. So this is the actual volumetric flow rate, mass density, heat specific ratios, and compressibility factor. So compressibility factor here is Z factor, and you can see it's empty. It might predict traces of liquid in the suction gas sometimes when you do the simulation. So you can use the vapor phase Z factor or the compressibility factor. And for discharge side, you can do the same. And for the performance, you should come to the compressor window and power demand, speed, polytropic head, polytropic efficiency, you can all find in performance. But remember, in this case, we don't have any information regarding compressor curve, so therefore we don't know which operational speed will be for each of the cases. And also for the efficiencies, we have one assumption, which was adiabatic efficiency of 75%, which was the default value here. You could alternatively use the polytropic efficiency of 75% or 80%. But anyway, those values are the initial guess, and later the vendor, based on their design and their offered compressor, they can revise the datasheet and update the values based on the actual compressor. For composition, you can use either the suction or discharge stream. You can find the composition in the worksheet tab and composition subtab. You need to repeat this process for all the cases in the datasheet. Thank you for watching this video, and if you have any comments, please write it in the comment section, and I will reply to it whenever I can. Have a great time, everyone, and talk to you next time.